Okay, guys, we are going to continue with our lecture on hemodynamic disorders, and we are going to pick up where we left off. On our last lecture, Hemodynamic Disorders 1, we were kind of finishing on this drawing component, and we basically were talking about giving you guys an appreciation of these Starling forces, right? These opposing forces that exist both in the capillaries and in the extracellular space, or the interstitial fluid, which kind of regulates what is pulled out of the blood and put into the cellular environment, and then what is pushed back into the bloodstream to basically be picked up as waste. And we gave you guys some examples about carbon dioxide and oxygen kind of being pushed out and pulled back in. And we know that hydrostatic pressure is a result of blood pressure. Also, another major component that regulates hydrostatic pressure is the abilities of arterioles and arteries and arterial branches to kind of adjust their pressure through vasodilation and vasoconstriction. So those things are happening in real time, where on the venual side or the venous side of things, there is far, far less regulation. So if we think about the capillary beds and the side coming in, which is the arterial side, there's much more regulation of pressure there versus once the oxygen is dropped off and blood is returning through the venual side, there's less regulation there. So a lot of edema, a lot of complications with edema occurs at that venual end because those vessels, they can't dilate and constrict as needed like the venual side. Like the arterial side. So, and I'll kind of draw your attention to that in a little bit. So what we're going to do now is we're going to kind of do a little bit of a deeper dive about some of the causations of edema, and I'm only going to give you about 4. And what I'm doing now is I'm setting up one group for your exam number 3, which is going to be a presentation based upon you and your partner's design. It has to be a video. It has to have visuals. It has to have. I will get you guys an instruction sheet that will tell you everything that I'm expecting. But I'm going to hand the comm over to you now, and you guys are going to tell me a thing or 3 about pathology. So let's dive into this lecture, and then when we get to the slide where I'm going to really kind of have you focus on for your exam 3, I'll stop there and we'll talk about it a little bit, and I will let you know what's coming down the pipe. And I will be grading all weekend. I just haven't had a moment to breathe. I have been so busy, and grading has been taking a major hit. So I apologize profusely, but there's only one of me, and I'm being tasked with 900 things and literally living in my office and the lab. So I'm going to put my little violin away so I stop playing the sad song, and we're going to get down to business. So let's talk about some of the things, some of the physiological changes that occur that make edema happen. And let's go with the first one here. So the first one is going to be increased capillary hydrostatic pressure. So I have here the capillary bed, and I told you that the arterial side here is well regulated because we know that these vessels and these branches here, they can open and close as needed. They're regulating blood pressure in real time. But on this end over here, we lose that capacity. We lose that ability because these don't have the smooth muscles that these do to kind of help regulate blood pressure in real time. So for example, just in case some of you guys don't remember, let me just kind of draw this. We know that vessels can dilate when needed, and we know vessels can constrict when needed, right? And what happens here is this event, I was looking for red, not orange. I've never seen a vessel like that. And let's make it look proper like a vessel. We know that this end of the branches here, this end of the arterial side, this is occurring in real time. And it's almost like when you're driving your car down one of these roads in Humboldt, you have your foot on the gas and you have your foot on the brake. And it's kind of an orchestrated thing that keeps the car from veering off the road and flying off into the ocean. So this end of delivery of blood is kind of dilating and constricting as needed in real time. It's never really stable in a single position. It's never stable in constriction. It's never stable in dilation. It's kind of going back and forth between these things. So anytime there's a rise in capillary pressure or there's a reduction of onconic pressure, we're going to have kind of this relationship here. We're going to have this loss of control. So if we have a rise in hydrostatic pressure, so let's say that this increases, right, and a decrease in onconic pressure, right, because we can lose proteins, and if we lose proteins, which I'll tell you about momentarily, we lose the control of the protein-based pressure in the vessel, right? So that's going to cause a mass exodus of goods out of the vessel. And then other things that can occur is if we have this increase in hydrostatic pressure. An increase in hydrostatic pressure, there's a lot of diseases that cause this. And we could have heart failure and renal disease. And when we have heart failure and renal disease, that causes volume expansion of blood. And that volume expansion of blood is going to increase hydrostatic pressure. Where when we have things like cirrhosis or heart failure, that can lead to changes in onconic pressure because your liver helps really regulate the albumin, right? The production of albumin protein. So the first thing to keep aware of is when we have a rise in hydrostatic pressure, especially at the venular end, at this end here of the capillaries, what starts to happen is, let me draw this for you guys so I can give you, where's my draw. Let's do this. The let's do a different color so it stands out. The endothelial cells, because you guys know that the endothelial cells line this, right? There's my endothelial cells, right? I'm kind of drawing them right there, right? So what happens is when we have an increase in this pressure because of some sort of hiccup in the physiology, these endothelial cells get further, see this, and further away from each other. So what that means is now there's a lot of goods that can leave the vessel, right? And it's unregulated. We don't want that to happen, but this is what happens when we have a complication, and that is where we have a rise in hydrostatic pressure, or we have, and that rise is greater than what the onconic pressure is, right? If you go back to our first week, I showed you that onconic pressure kind of let me clean this up so I can kind of draw it a little here. Onconic pressure kind of stays the same throughout, right? It doesn't really change. And hydrostatic pressure, as we get closer to the venule side of things, hydrostatic pressure begins to decrease, right? And as it decreases, it goes below what the stabilized onconic pressure is. And I'm just going to draw this as like onconic pressure, right? It's just kind of stable across the entire width of the vessel. And this difference between, as you can see here, this drop here in hydrostatic pressure basically allows the onconic pressure to be greater, right? So it's now we have a greater onconic pressure, and that's what pulls things back inside. But when we have a complication and that hydrostatic pressure doesn't dip here like it should, let's say it's maintained, and you can see now that it's maintained at a level that is higher than the onconic pressure, so it's going to keep pushing things out, right? So that is how, and I'm just going to draw some arrows here, that is how hydrostatic pressure can overpower onconic pressure, and we can have a mass exodus of goods across the entire duration of the vessel. So now when this happens, we have minimal to no reabsorption of the fluid at the venular, at the venous end, and I've already kind of told you that. So, well, I did not want that. I wanted this. So then we basically get edema, right? So if we have a complication, such as anything that disrupts volume balance of blood, especially anything with the kidney or the heart, we can have this this problem here. And also, I'll tell you a little bit more about this in a second. This is the lymphatic system, right? And the lymphatic system it acts as a drainage system for when we push things out of the vessel and into the interstitial fluid. So we'll talk about the lymphatic drainage system momentarily, but this too can lead to problems. So if we have an increase in hydrostatic pressure, and as a result of that increase in hydrostatic pressure, we just have things being pushed out all the way across the capillary bed, right? So this is where we kind of divide that line and things start to get pulled in here. And here we have a mass exodus of things out. But if we have an increase in hydrostatic pressure, that changes everything. We will continue to push out here and here and here, right? So things will still go out. Now, if that happens, we can have issues with the lymphatic system trying to drain that excess fluid being pushed out and all the proteins being pushed out. And we know proteins can be pushed out because, as I said, when we have an increase in pressure, these endothelial cells, they start to get further and further apart. I'm going to show you guys a picture of that in a moment to show you how those gap junctions get bigger, right? And then we can get all these protein-rich fluid pushed out. So this can lead to edema. So that's kind of like mechanism 1. Now, mechanism 2, excuse me, would be a reduction in plasma onconic pressure. So this occurs in the case when we have hypoproteinemia. So hypoproteinemia would be when we have, for some reason, there is a reduction in protein production, and generally it has to do with albumin production. So when we have a loss of total protein concentration or a fall in serum albumin, we get hypoproteinemia. Normally, albumin accounts for almost, I'm going to say albumin. I'm just going to go out and just say it. Albumin in the blood counts for about 50 to 60% of total protein in the blood, right? That's not bad. It's my right hand, guys. It's looking pretty good. Okay. So when we look at, let's go back to this. When we look at, let me clean this for you guys. When we look at this onconic pressure, right, which I told you is maintained at almost an equilibrium across the entire duration of the capillary bed, right, because it's protein dependent. When 50% of that onconic pressure is maintained, oh, that was an awful 5. That was awful. So that looks like I had a stroke midway through. Okay. I can't do that to you guys. I can't do that to myself because I have these weird OCDs that let's just put that in there and make it look pretty. There we go. Isn't that prettier? When we have 50% of this protein that is maintaining this equilibrium, right, or this onconic pressure, when we have a dip in that albumin for whatever reason, well, then we're going to have a reduction in onconic pressure, right? So let me just kind of draw this to make it a bit more clear. So if we have cirrhosis or some sort of liver complication, then this onconic pressure this line is just representing a level, right? This onconic pressure is now going to drop substantially because the proteins that are maintaining this pressure in the blood have dropped substantially. So look what happens now. If we have hydrostatic pressure, and hydrostatic pressure is here, and we know it's supposed to drop, and it begins to drop, but it's still higher than that onconic pressure, right? Because here's the new onconic pressure because we lost that albumin. Well, then what happens is all across here, we have a mass exodus of goods being pushed out of the blood vessel, and we lose that counter force. We lose that counter onconic pressure. So we don't have it anymore. So when we have a reduction in albumin synthesis in the liver, or we have protein malnutrition, this leads to a fall in onconic pressure, and then we have a net movement of things outward. And then we basically have edema. And one of the major complications that we see this physiology in is something called nephrotic syndrome. And this is the most common and important disease that occurs as a result of loss of onconic pressure. And this basically leads to when we have nephrotic syndrome, when we look at, let me kind of zoom in here. So we look at the kidney, right? And we see that in this kidney here, we have a normal nephron. And in this kidney here, we have a nephrotic syndrome. So we have a nephron that's not functioning right. So what happens is in a nephrotic syndrome, the blood and the waste and the protein, because there's damage here in the nephron, these big proteins are allowed to leave and go into the urine, right? Where when we have a healthy kidney and a healthy nephron, those proteins are contained in here and they're reabsorbed back into the body. So let's see if I can zoom in on this. So when these proteins escape the kidney because of issues, because of a disease or trauma or infection or whatever, all these proteins get into the urine and they leak out. So if they're leaking out of the blood and going into the urine, we lose onconic pressure. Here you can see these large proteins enter the kidney and then they get reabsorbed back into the blood because we don't have any damage or any sort of complications here. But when we have nephrotic syndrome, those proteins can pass through and then enter the urine, and now you have high levels of high levels of protein in your urine. And when you lose the proteins in the urine, what's going to happen is your onconic pressure is going to look like this. Okay, if you start losing it in the urine, your onconic pressure is going to stop because your kidney is not reabsorbing those proteins. So if we kind of just say, okay, well, if we have that loss in onconic pressure, but hydrostatic pressure is maintained and hydrostatic pressure still drops as it should, but look at this, that pressure is still greater, right? Because so much of that protein is being sent out into the urine. So this is an example of where a complication can lead to a loss of protein in the urine rather than being reabsorbed back into the bloodstream. All right, so this is one we've already discussed in previous lectures. So we've already kind of talked about how one of the first responses that occurs in inflammation is vasodilation. And then when we have vasodilation, we have increased blood vessel permeability, where we know this protein-rich fluid can kind of seep out into the interstitial space. So as you can see here, inflammation, we have capillary endothelial injury by toxins or whatever the mechanism or whatever the catalyst is for inflammation. We know that histamine is one of the major chemicals released by mast cells. We talked about that. And then we have an increase in blood being pushed to the site of injury because histamine is going to cause vasodilation. So we know that. So let's just do it again just to kind of make sure everybody's understanding. This has been a very quiet class. So when we have histamine released, we go from something like this to something, and this is just if we're looking straight into a capillary, or a blood vessel, right? So we have this, I gotta make it look nice because my OCD will drive me mad. So we go from something like this to this. And then when we have an increase in this diameter of this blood vessel, we are going to have greater permeability of the endothelial cells. So remember on that last drawing, I had green and I said, yeah, we have the endothelial cells, draw, listen to me, draw. Okay, we have endothelial cells that look very close together, right? And then we know that these are held together by these proteins here. And then when we have this dilation and we have greater blood volume, we know that these endothelial cells get further and further apart, and that's what allows the protein-rich fluid to enter the interstitial space, right? And you can see that same thing here. We can see that we kind of lose that little junction there becomes increased in size and things can get through there. So you know this one very well. I'm going to show you a picture in a moment that just kind of reiterates it. So this endothelial cell gaps, they increase. You can see that here. You can see that here. I also drew that up here. We talked about the endothelial cell gaps getting wider, right? So I'm just kind of beating a dead horse here. This leads to capillary permeability, to plasma proteins. So I told you this protein-rich fluid can leave. And when protein leaves the vessel, right? Here's the vessel. When protein leaves, what happens to onconic pressure? When we have normal endothelial cell function and there's no gap between these cells, onconic pressure remains the same, right? But then when we have a histamine and then we have an increase in the dilation of the vessel, then onconic pressure is going to drop because we're going to have greater permeability of the endothelial cells, and then protein can leave the vessel. And what's going to further push that is we're going to have hydrostatic pressure that across the capillary is still going to be higher than onconic pressure, right? So all of these events are just going to push more things out, and we're going to get swelling, and the swelling is going to look red and irritated because we have this mass exodus of this protein-rich fluid, and we have a loss of onconic pressure. And in this case, we might have a slight increase in hydrostatic pressure, right? So these are just different mechanisms. Inflammation is the catalyst, but again, very similar response by the endothelial cells in the capillary bed. So let me clean this up a little bit. And then I have this here because this is something that you've seen before in a previous lecture. So same thing. When we have histamine released, we have this dilation. You can see that this is much larger than this, right? We have permeability of the endothelial cells. They get further and further and further apart. And I told you earlier that the regulation of edema on the arterial side is greater than the regulation of edema on the venous end or the venule side. And that's why we have the pushing out of fluids here on the venule side, because it can't regulate that process as well. So you can see here we have that fluid being pushed out, and we have protein-rich content in here. And as more proteins get pushed out, what happens to the onconic pressure across this entire system here is onconic pressure, because of the loss of protein, begins to drop. Right? So you guys see that, and hydrostatic pressure, even if it begins to drop, here's hydrostatic pressure, even if it begins to drop, it's still higher than the onconic pressure, which is going to cause more of that stuff to be pushed. So that makes sense, right? That's pretty easy for you guys. Okay, so now we're going to talk about this lymphatic system. Okay, let me clean this up momentarily so everything makes sense. Okay, so I told you that in every picture you look at with the capillaries and the lymphatic system, they're always kind of within proximity of each other because this is a drainage system for this. So together with the blood vessels, the lymphatic capillaries also function to ensure that circulation through the surrounding cells and tissue is basically sufficient. It basically ensures that each cell gets enough nutrients, and it also ensures that the cells and the tissues are drained so that fluid balance is constant. Okay, so this is like your drain in your bathtub, right? If you keep filling up that bathtub and you don't undo the drain, then the bathtub's going to overflow, and that would be essentially edema, right? An overflowing of fluid. So when there's any sort of impairment of hydrostatic pressure and onconic pressure, then we also have impairment of the ability of the lymphatic system to drain these fluids. So then we can get something called localized lymphoedemia. And lymphedemia is basically impaired blood flow of the lymphatic, or not blood flow, I'm sorry, it's impaired flow of the lymphatic system that causes basically swollen extremities. So you can this drainage issue can also cause things to swell. And let me show you a picture of that. Okay, this would be the type of swelling versus a normal arm, right? So if we have blockage or any sort of impairment to the lymphatic system, that as well can lead to a type of edema where we could have normal function here, normal hydrostatic pressure, but then we have this blocked system here, and what that's going to do is it's going to shift the pressure relationship out here in the interstitial space. Because remember I told you there's hydrostatic pressure here and there's hydrostatic pressure here. And there's onconic pressure here and onconic pressure here. But then once you start pushing all this fluid out and we have a buildup of fluid here, that can disrupt this entire relationship. So and let me see what else I can tell you about this. So this lymphedema basically just results from impaired flow of the lymphatic system, and the symptoms are basically swelling to the extremities, and these can range from mild to severe, and to someone becoming disfigured by this. So this is another way we can this is another mechanism that we can basically see which causes edema. Okay, so now I have given you a couple of mechanisms, okay, to think about. Here is your exam 3. One group is going to get this, and another group is going to get one on free radicals. And your exam, like I said, I will get you a detailed sheet about what I expect from you. And what you guys are going to do is you are going to give me a presentation on either sodium water retention, which basically leads to the activation of certain things like angiotensin and renin and angiotensin 2. And the other group is going to get one on free radicals. So here is your exam 3. I don't know why that's there. Let me get it.
I'm still not sure about that.
And even Siri is unsure about that. I don't know what she's doing, but she just showed up to the party.
I'm sorry.
We're not talking to you. Don't be sorry. When we have too much salt, especially in disease states, edema occurs primarily because of the body's retention of too much salt. This is why when people get metabolic complications or heart disease or diabetes or any sort of potentially harmful development of a disease, we lower the salt or sodium chloride, right? This is because the excess salt can cause the body to retain water, okay? And not only can the body retain water via salt and via diet, but when we have issues with the heart or the kidney or the liver, like we do in most diseases, especially diabetes, they're all impacted by that. Well, we're already at risk for developing edema just because of the complications that are associated with diabetes. And then when you add salt to the diet, which most Western diets are rich in, now you're increasing the potential for developing pretty severe edema. So when we have this excess salt, the body will retain water, and that water will essentially leak out into the interstitial space where it will appear as edema. And medications can also cause this edema as well. So we have to be very, very careful when we enter a disease state between this salt and water balance and these medications that are being used. So excessive retention of salt will increase hydrostatic pressure. And this happens because the expansion of intravascular volume, blood basically, occurs. And we all know that salt, water follows salt. So if we have salt, water is going to be retained, and this is seen in a variety of diseases. So some of these diseases are renal function diseases and renal failure diseases. So what I'm tasking you with is explaining this process to me. If we have hypovolemia, okay, and basically hypovolemia is just maintaining water due to excess sodium. which basically leads to the expansion of the extracellular space compartment or the interstitial fluid. And it basically overloads that interstitial space. So this is typically due to kidney retention of sodium and water. So when we have this condition, we have all of these mechanisms that are involved in this process. One of the things that happens is renal vasoconstriction. So the blood vessels within the kidney are going to constrict. We have the release of renin and aldosterone, and I want you guys to tell me what this is. And then we have the retention of water and salt, and this leads to edema. I have this here, which basically tells you about that renin, angiotensin, aldosterone pathway. And what I want you to do, and I will draw this out in a much clearer explanation when I upload the lecture and your expectations for the exam, is I want you to consider hemodynamic disorders. I want you to present to me what they are in a very similar fashion that I did to you. I want you to tell me what are some of the mechanisms that are involved in this disorder, right? Look what I did to you guys. I gave you guys so many different kind of representations of how this condition can come about. But what I want you to do is focus on this, and I'm gonna be just kind of very vague about this slide because this is your exam. You and your partner are going to have to figure out how you want to present this to me. It's going to be a video. It's going to be about 15 minutes, and I want you to explain mechanisms to me because this is a graduate level class, and now I want you to think mechanistically on a cellular level, and I want you to think about these other systems that are involved in creating complications, right? This is a multi-system complication. If you don't know what GFR stands for, you need to look it up. It just means glomerulus filtration rate, but you need to look these things up. You need to be able to speak this language, and I'm going to give you plenty of time to do so. So you need to explain this to me, and you need to explain this to me, and I'm looking for details. So I will get that information out to you. I'm going to be vague on this slide, and let's move on. Okay, so essentially at the end of the day, we have this inflammatory edema, which I showed you here, right? This could be caused by any sort of toxin, drug, injury, whatever. And this edema is slightly different than non-inflammatory edema. And non-inflammatory edema would be these other things I've been showing you, right? So increased capillary hydrostatic pressure, decreased onconic pressure, sodium water retention. Those would be non-inflammatory. Lymphatic obstruction. So there's essentially two types, okay? And generally this one, if it's an injury, it's going to be acute, all right? It's going to be on and off and done. Where these guys here, these could be a result of several systems kind of faltering simultaneously. Okay, and what I have here for you guys is just kind of two different versions of the same story. So this is anasarca. This is a condition where you have overall swelling throughout the entire body. Several reasons can lead to anasarca. But one of the most common causes of this is clinical heart failure, cirrhosis. So we know that this would be caused by an increase in hydrostatic pressure, and if we have an issue with the liver, we're going to have a decrease in albumin production. So this is going to be a result of a decrease in onconic pressure. So this would be the decrease, because if we have liver cirrhosis, we're going to have issues with albumin. This was the original line of onconic pressure. And an increase in hydrostatic pressure, right? And even if the hydrostatic pressure drops across the capillary beds as it should, it's still way higher. So this is going to cause mass swelling throughout the entire body. Other causes of this condition can be venous obstructions, burns, trauma, malignancy. So a lot of things can kind of cause this anasarca. And this would over here would be an inflammatory edema, and this is a really extreme case. So you can see this person's normal appendage and then the swollen and the injured appendage there. And I have this slide here just to kind of show you, to kind of go back between this here and this here. We have these two different types of fluids that are released in edema into the interstitial space. And I remember when we talked about inflammation, we talked about that a little bit here. So when we have inflammation, we have this protein-rich fluid that's pushed out, because when we have inflammation, we have greater, so here's our endothelial cells, right, under normal conditions. And then when we have inflammation, those get further and further apart. And these are cells, right? I'm just kind of drawing them flat. You're looking at these flat, right? And that allows the protein-rich content to get into the interstitial space. So you can see here that this anasarca and this inflammatory edema are really kind of defined by what sort of liquid is pushed out. So we have this transudative and exudative liquid. This one here occurs mostly when we have an increase in hydrostatic pressure or low onconic pressure. And you can see here that the proteins generally stay inside of the vessel where we have the liquid or the water within the blood pushed out, right? And you can see that here, right? But when we have inflammation and we have this side over here, this occurs when we have inflammation and increased capillary permeability, right? So as I showed you in my drawing, the capillaries kind of have those Swiss cheese holes in them, right? Let me see if I can draw that for you guys. Let me clean this up a little bit. I'm going to let you guys can go back and look at my lecture because I need to wrap this up. But anyways, you can see on this one here that the endothelial cells are further apart from each other. You see that space? And that allows the proteins in the vessel to come out. Okay, this is high protein. This is low protein. Okay, and that's the difference between a non-inflammatory and an inflammatory response. So it kind of has to do with what is pushed out. And of course, I would like you to tie all of this into your presentation that you're going to be giving for me. I would like for you guys to really tie in all these factors, and I will be looking for that. So let's move on to what hyperemia and congestion are. Let's just kind of go over some of these terms. So hyperemia and congestion. So hyperemia is basically a condition that is identified as an increase in arterial dilation and an increase in blood inflow. Okay, and this occurs in exercise and skeletal muscle. This is something that happens when we're doing exercise. So hyperemia is an active process resulting from augmented blood flow due to arterial dilation. So guys, when you guys are running or you're lifting or you're exercising, your arteries, remember I told you they have the ability to constrict and expand. So when we have hyperemia, this basically is the expansion of those blood vessels, and this is kind of where I'm bringing exercise in. This happens at sites at skeletal muscle, right? Because as the muscle is demanding more nutrients and more oxygen, that means that the heart is going to be pumping harder, right? Because whatever exercise we're doing, the heart is going to increase heart rate. You're going to increase blood flow, and then those vessels that are going to deliver the oxygenated blood, they have to adapt and increase in their size. And that way they bring in more blood, right? So we have greater volume of blood because we know our stroke volume's increasing, we know our ejection fraction's increasing, we know heart rate's increasing. Therefore, we're going to have more blood being delivered. We're going to have to, the muscle's going to demand more. Oh, that's a horrible color. Let me see if I can find a better one for you. Let's do that. The muscle's going to require more oxygen to be delivered, so I'm going to draw oxygen in there. The muscle may require more glucose. So let me draw some glucose in there. Glucose is always green in my mind. So when the vessel basically expands, we're going to get a greater delivery of those goods to allow the muscle to keep contracting. And congestion, on the other hand, this is when movement of these things are impaired. And this can be impaired at the venous end, right? So when I keep showing you this, let me find that one picture here. We generally have, and let me clean this, we have impairment, or we have edema that most commonly occurs at the vascular end over here. So that's where congestion can occur. And this can occur, this can impair the tissue, this can impair blood returning, this can cause heart failure, this can cause isolated venous obstructions. So when we have congestion for some reason, an impairment of movement, that leads to some complications that can impact, again, the entire system. Oops, I just wanted to erase that. I didn't want to move it. That looks kind of cool. That's spacey. Yes, so there is kind of a just hard and fast explanation of what hyperemia and congestion are. And I'm just telling you because you might want to use it. You might want to use it in your lecture that you're going to tell me. And here's just another kind of slide to help you with the congestion. Congestion and edema commonly occur together. You can read this. I'm not going to read that for you. You can read this as well. Hyperemia versus congestion. You guys can handle that. Maybe it's useful for your paper or for your presentation. Maybe it's not useful. Hemorrhaging. Let's talk a little bit about hemorrhaging. So hemorrhaging is a pretty serious form of edema. It can happen in the brain. It can happen in the aorta. And this is a massive, massive blood loss where you can see here this picture. We have a break in the integrity of the vessel, and this can lead to severe blood loss, severe protein loss within the blood, and just overall systemic loss of blood pressure. So this is basically defined as a massive exodus of blood flow from the vessel. And it's most often the result of damage to the blood vessel or from defection of clot formation. So we could have poor clot forming, or we could have trauma, right? So football players, they receive a tremendous amount of trauma. MMA fighters receive a tremendous amount of trauma, especially to the head. So trauma could cause this, but also disease. So when we get things like atherosclerosis plaque, and we have a buildup, and then we have, let's say we have, let me just draw this here to give you a visual. Let's say we have plaque building up here, right, in the aorta, or down here, right? We just have plaque building up. It's just a visual. This is going to increase pressure where that plaque formation is being built, and then ultimately this vessel, it can only withstand so much pressure. Hydrostatic pressure is going to be increasing tremendously, and then we will have a break of that vessel, and then a tremendous amount of fluid, protein, red blood cells, white blood cells, everything just seeping out, leading to systemic failure of pressure, and that could be devastating to a body. In the case where trauma is induced by atherosclerosis or inflammation or inflammatory process, we could have erosion of the vessel walls, which can lead to hemorrhaging. So we can just say that this could also, we could have erosion here, right, because of trauma from atherosclerosis, and not just atherosclerosis, but again, all these neutrophils that are trying to clean it up and fix it. All of these macrophages that are trying to clean it up and fix it. That repair damage cycle that is occurring when we have the development of atherosclerosis, it starts to weaken the integrity of the endothelial cells, and that can lead to damage and hemorrhaging as well. Let's do this one here. We could have strokes that occur in the brain due to hemorrhaging, and you can see here when there's alterations in pressure, this can impact the very delicate vessels within the brain. and we can have a burst of the vessels causing bleeding in the brain, which will increase pressure, which will basically begin to destroy neurons and have an impact on certain parts of the brain, depending on where the bleed is. And you can see here that the brain already has very, very, very little space between the skull, the gray matter, and the water. So when we do have a burst here and we do have blood seeping into the brain, the pressure is tremendous. So these would be other forms of edema that are a bit more extreme. Let's talk about a hematoma, because a hematoma is another version of sort of edema, but this one would be caused by trauma. So we could imagine that a hematoma is going to be an inflammatory response as well. This is generally defined as a collection of blood that is outside of the blood vessels, as you can see here, because of the bruising. So this is under the edema banner. And most commonly, hematomas are caused by an injury of the vessel wall, so very similar to hemorrhaging, but not as extreme. And when we have this damage to the vessel wall, this promotes the blood to seep out of the vessel into the surrounding tissue. And hematomas can result from an injury of any type of vessel, whether it's artery, vein, or capillary. So this doesn't just occur at the capillary beds like some of the edema does. Something that's really kind of interesting is the athletes that I deal with. Let me show you some super interesting hematomas. Look at this guy. This is someone who actually was fighting in Thailand. He was fighting a Thai champion and basically took an elbow to the side of the head. And look at the hematoma that he developed there. It's absolutely absurd. This is a real picture. And the kid kept fighting. So they actually had to stop the fight because he wanted to keep fighting. But if the person that he was fighting kept elbowing like he did, this thing would eventually pop open and they would have a much bigger injury on their hand if that was to actually burst. Again, you have fluid, or you have material from the blood vessel entering into the interstitial space and causing swelling. Here's another one from some fighters in Thailand. This is due to leg kicks. So you can see that there's mass trauma when these fighters kick their legs. You have this hematoma here. This is covering the entire side of the leg. You have some inflammation. You can see that you have some blood that is oxidizing here. That's why you have that change in color. And ultimately, the body will reabsorb some of this and clean it up. So it will look brand new like this over here. And then here's another one from a fighter who took some pretty nasty leg kicks. And you can see this hematoma is just massive, right? So this thing can kind of look like this, or it can look like this and this. Now, there's one more little thing I wanted to talk about, which is kind of in the edema family. And this is the muscle pump. So you guys know very well when you're in the gym and you start doing your arms and you start doing your chest, you look far more swollen in the mirror after you do the exercise than you did when you came in. And we know that's called like the pump, right? All the bro science are like, yeah, bro, I got my pump. And this is kind of a form of edema, and we call this transient hypertrophy. And it's transient because it's the size of the muscle is really just, it's getting bigger because it's being engorged by fluid. And where's that fluid coming from? Well, most of that fluid comes from the blood, right? So when we're exercising, you think about when you're strength training, you have these muscles just squeezing the vascular system, right? And then when you contract, it squeezes the vascular system. When you release, it lets the vascular system go, and you have these shifts in pressure, specifically diastolic pressure. So what happens is, I mean, you guys all probably all know this, right? When you're doing a really heavy lift and you drop the weights and you're lightheaded, well, that's because you have the occlusion of blood because the muscles are contracting around the entire vascular system. And then when you drop the weight, you have this release of the blood, and the entire time pressure has been building. So this transient hypertrophy is essentially a form of edema. And I wanted to throw it in here because it's not well studied, but we know that the muscle pump is it's kind of slang, right? And it's slang for this phenomenon that we call transient hypertrophy, and this basically just refers to the growth of muscle, and it's done so in this transient and temporary manner. So it's a pretty complex process, but just to keep things quick here, this occurs when fluids, including water and blood, accumulate in the muscle during movement, and it happens basically in response to two triggers. So one of the triggers is lactic acid, and when lactic acid or lactate in hydrogen, whatever you want to call it, begins to build up while you're working out, this draws water into the muscle. So lactate and hydrogen will draw muscle in, so the muscle will begin to swell. And where does that water come from? Well, it's coming from the blood, and it's coming from the interstitial space. So now you have this net movement of water into the muscle, and the muscle becomes engorged. And your heart muscle pumps more blood to the working muscles. This is the second trigger, because they need more oxygen and nutrients to power them. So this surge of fluids causes your muscles to swell, making your muscles look bigger than they are. And we call that the muscle pump, right? So this is kind of in that realm as well, because the fluids are coming from somewhere else, and we're shifting them from both the interstitial space and perhaps the capillary beds into the muscle, and the muscle is retaining that water. So just kind of keep in mind that this is very common, because your muscles, primarily 70% water. So when you're working out and you have this muscle contraction and heart rate increasing, and we know if heart rate increases, we're going to have vasodilation of the arterioles, and we're going to have more blood pushed to the muscles, and we're going to have more fluid seeping out into the interstitial space, because with increase in heart rate, we're going to have an increase in hydrostatic pressure, right? But there's no changes to onconic pressure. Onconic pressure is going to stay the same because we're not losing proteins anywhere. So we just have this mass shift of water from the interstitial space and the bloodstream into the muscle, where now the muscle is going to look bigger because it's retaining more water. So that's all I have for you guys. This is Hemodynamic Disorders and Edema Lecture 2, and I will get your exam material to you momentarily.